Hello students, welcome back to the classroom point. In our previous class, we have discussed the theory part of the hybridization and its principles along with the SP hybridization examples. So in today's class, we shall discuss the both SP2 and SP3 hybridization and its examples. So let's begin the class now. SP2 hybridization. So in SP2 hybridization, one s orbital intermixes with two p orbitals to produce altogether three equal energy SP2 hybrid orbitals. So let us see that examples. This is s orbital. P orbital, you can take px orbital, py orbital or pz orbital. Any combination we can consider it. So it will produce the three orbitals with equal energy. Plus and minus lobe of this hybrid orbital. Plus and minus lobe. Here this is plus and minus lobe. So these three are called as the SP2 hybrid orbitals. These SP2 hybrid orbitals arrange in the trigonal planar shape. Bond angle is 120 degrees. So usually molecules which participate in the SP2 hybridization, their shape is planar. So that we can call this one as a trigonal planar shape. Let us take an example here. Boron trifluoride molecule. So in boron trifluoride molecule, the central atom is boron, atomic number 5, electronic configuration 1s2, 2s2 and 2p1. So only valence electrons participate in the hybridization valence orbitals. So here boron is having only one unpaired electron. With the help of this unpaired electron, boron is able to form only one boron fluorine bond. But here boron fluorine bonds 3 are present. So to form 3 single bonds, boron must need 3 unpaired electrons. Hence, one of these s electron jumps into the p orbital, giving the first excited state electronic configuration. So after jumping of this electron from the lower energy orbital to the higher energy orbital, we get the 3 unpaired electrons. Now this one s orbital intermixes completely with 2 p orbitals and produces 3 sp2 hybrid orbitals. So let us take the boron 3 sp2 hybrid orbitals. So these are the sp2 hybrid orbitals of boron. Each of these orbital is occupied by the unpaired electron which is present in this area. And later, fluorine atomic number 9, electronic configuration helium 2s2, 2p5. So in the last orbital, there is a one unpaired electron present in the p orbital. So the fluorine p orbital with unpaired electron now overlaps with the sp2 orbital of the boron and to produce p orbital of fluorine to produce the boron fluorine single bond. In this way, remaining 2 fluorine atoms also their p orbitals overlap with the sp2 orbital and produce finally altogether 3 boron fluorine single bonds. So here we can get that boron, fluorine, and fluorine. Bond angle is 120 degrees. Shape is, as I said earlier, it is a trigonal planar shape. Here 3 sigma bonds are present. The sigma bonds arise 3 boron fluorine sigma bonds are present. These are arised by the overlapping of the sp2 orbital of the boron with the p orbital of the fluorine. So we can call these sigma bonds as sp2p bonds. This is one example. Let us take the ethylene molecule. One more example. C2H4. Ethene or ethylene molecule. So ethene molecule, every carbon atom participates in the sp2 hybridization. So let us see its electronic configuration: 1s2, 2s2, 2p2. Valence orbital, only 2 unpaired electrons are present in the p orbital. One of these s electron jumps into the p orbital and produces the altogether 4 unpaired electrons. Carbon always forms its chemical bonds only in the first excited state, because in first excited state only it will have the 4 unpaired electrons. So now here carbon undergoes sp2 hybridization. That means 1 s orbital, remaining 2 p orbitals undergo intermixing and produce the equal energy of the 3 sp2 orbitals, leaving 1 orbital unhybridized. That orbital participate in the pi bond formation. So now let us see here. These 3 are sp2 orbitals of carbon, in which each orbital is occupied by a single electron. See that this diagram and this diagram both are same, just only we turn this diagram. So this lobe comes here, these 2 lobes goes here and there. And another carbon atom also participates in the same hybridization, so that one of the sp2 orbital of the other carbon atom overlaps with the sp2 orbital of this carbon atom, providing the carbon-carbon single bond. These are the remaining 2 sp2 orbitals of other carbon atom. So they are also occupied by the single electron. So this single bond is arised from the carbon-carbon single bond arised by the overlapping of the 2 sp2 orbitals. Next, unhybrid orbital is left with every carbon atom, that we can represent like this. Imagine this is a px orbital or any px or py or pz. You can take any one combination. So these are having the unpaired electrons. The overlapping between these 2 unhybridized orbitals produce one carbon-carbon pi bond. So in the carbon-carbon pi bond electrons are located above and below the sigma bond electrons. That means above and below the internuclear axis. sp2 orbital of every carbon atom. Now every carbon atom is left with 2 sp2 orbitals. Here 2 are there, here 2 are there. So each sp2 orbital overlap with the 1s orbital of the hydrogen to produce carbon hydrogen sigma bonds. So like that we get altogether 4 carbon hydrogen sigma bonds. So here we can observe that sigma bonds are of 2 category and pi bond is of 1 category. So here one sigma bond, carbon-carbon sigma bond is arised from the sigma sp2 overlapping, And carbon hydrogen sigma bonds arised from the sp2s overlapping. Carbon carbon pi bond is arised from the overlapping of the p orbitals. Px and px I have taken here. You can take the py or pz. Now here hydrogen carbon hydrogen bond angle in the ethylene molecule is 117.6 degrees. Carbon hydrogen carbon carbon, this bond angle is 121 degrees. Carbon carbon double bond length is taken as 134 picometers. Carbon hydrogen bond length is taken as 108 picometers. So in this ethylene molecule, 4 hydrogen atoms and 2 carbon atoms all are present on the same plane. That means in the plane there are 6 atoms in this ethylene molecule. What is the percentage of the S character and P character? That means percentage of the orbital character for the sp2 hybrid orbitals. So percentage of the S character orbital character equals to 100 divided by number of hybrid orbitals, that is 3. That means 33.33 percentage every orbital. So here one s orbital is present in the sp2 hybridization. So percentage of s character is equals to 33.33 percentage, and percentage of p character, there are 2 p orbitals are present, so multiplied by 2, approximately 66.67 percentage can be considered. So this is about the sp2 hybridization. Now let us see the sp3 hybridization. So in sp3 hybridization, as written here, one s orbital intermixes with the 3 p orbitals. So here one s orbital intermixes with all 3 p orbitals, that means px, py and pz orbital, to produce totally 4 equal energy sp3 hybrid orbitals. So we can take the diagram also. S orbital intermixes with px orbital, py orbital and pz orbital to produce 4 orbitals of equal energy. These are called the sp3 hybrid orbitals. These 4 sp3 hybrid orbitals are arranged around the central atom in a space to minimize the repulsions and gives tetrahedral shape. So the shape of this orbitals is tetrahedral arrangement. These are all sp3 hybrid orbitals, each sp3 hybrid orbital. So bond angle between these orbitals is 109.5 degrees. So let us take few examples that participate in the sp3 hybridization. So first example is methane molecule. So as I said earlier, carbon always participate in the bond formations in only first excited state. So it's first excited state electronic configuration I am writing directly here, having the 1 2s electron and 3 unpaired sp3, so 3 unpaired p electrons. Now this s orbital intermixes with the 3 p orbitals and producing the 4 sp3 hybrid orbitals. So that orbital shape I am writing here. Each of these sp3 orbital is occupied by single electrons. This is about the carbon. So sp3 orbital of the carbon now overlaps with the 1s orbital of the hydrogen in this fashion to produce altogether 4 carbon hydrogen sigma bonds. So here carbon, the bonds are arranged like this. Hydrogen, and these are all hydrogens. So that gives a tetrahedral shape. So totally 4 carbon hydrogen sigma bonds are present. These sigma bonds are raised by the overlapping of the sp3 orbital of the carbon with s orbital of the hydrogen. The bond angle, as I said earlier, it is 109.5 degrees. Shape is tetrahedral. So let us take another molecule, NH3 molecule, ammonia molecule, in which the central atom is nitrogen, having atomic number 7, electronic configuration 1s2, 2s2 and 2p3. So it has a pair of electrons in s orbital and 3 unpaired electrons in the p orbital. So now it participates in the sp3 hybridization. Here pair of electrons also participate in the hybridization, so that you will get the 4 sp3 hybrid orbitals. So in this case, this is sp3 orbital, and here like this. Among all these 4 sp3 orbitals, one of the sp3 orbital is occupied by the pair of electrons. Rest of the sp3 orbitals are occupied by the unpaired electrons. So these sp3 orbitals of the nitrogen overlaps with the 1s orbital of the hydrogen and produce 3 nitrogen-hydrogen sigma bonds. So here its equivalent structure we can show like this. Lone pair of electrons are present. So while saying the shape of the molecule, we don't consider the lone pair of electrons, we consider only the bond pair of electrons, so that it looks like a pyramid. Hence the shape is called the pyramidal shape. Since 3 corners are there, it can be called as trigonal pyramidal shape. And bond angle in this ammonia molecule is 107 degrees. See, in both of these cases, hybridization is same, but the bond angle in this case is less than the bond angle in this case. Reason is here, this lone pair of electrons repel this bond pair of electrons, so that bond pairs are pushed closer to each other. Hence, the angle between the bonds decreases. In this case, lone pair of electrons are not there. That's why bonds are little bit arranged away from each other. But in that case, that chance is not present. Now, let us take the third molecule. That is water molecule, in which oxygen is the central atom having the atomic number 8, electronic configuration 1s2, 2s2 and 2p4, a pair of electrons in both s and p orbitals and 2 unpaired electrons in the p orbital. So it is having the 2 pairs of electrons and 2 unpaired electrons in its valence orbit. Now it participates in the sp3 hybridization and produce 4 sp3 hybrid orbitals. So here these are 4 sp3 hybrid orbitals. In that, this is of oxygen. 2 sp3 orbitals are occupied by the lone pair of electrons and remaining 2 are occupied by the single electron each. And these overlap with the 1s orbital of the hydrogen and gives 2 oxygen-hydrogen sigma bonds. So its equivalent structure we can write down as oxygen, here hydrogen is present, here 1 lone pair of electron, and here also 1 lone pair of electron is present like this. Now, since 2 lone pair of electrons are present, this molecule involves lone pair, bond pair and bond pair repulsions. All type of electronic repulsions are present in this molecule. As a result, since lone pair repulsions are stronger than the other type of repulsions, so these lone pair repulsions causes the lone pairs to go away from each other. Then obviously these 2 lone pairs will push the bonds of these hydrogens to come closer to each other. Hence, bond angle in water molecule is reduced to 104.5 degrees. So from this it is very clear that even though these are all participating, methane, ammonia, water in the same type of hybridization, but the bond angles are not equal. Reason is, here no lone pair of electrons are present. Here one lone pair of electron, here two lone pairs of electron. So whenever number of lone pair of electrons increase, automatically electronic repulsions increase and bond angles gradually decrease. And from here to here, bond angle decreased by 2.5 degrees for one lone pair. And from here to here also again the bond angle is reduced by 2.5 degrees. That means we can imagine that molecules having the equal number of the valence electron pairs, then for every one lone pair of electron increase, the bond angle can be reduced by 2.5 degrees. Now let us take the one more molecule, that is ethane molecule, CH3. Ethane molecule. So in ethane molecule, every carbon atom directly participates in the first excited electronic configuration. I am writing here. So participate in the SP3 hybridization. (2p3), s orbital 1 electron and p orbitals 3 unpaired electrons. So every carbon atom participates in the sp3 hybridization provides the 4 sp3 hybrid orbitals. Now these 4 sp3 hybrid orbitals we have to arrange. See this diagram we have to rotate like this. So one of this sp3 hybrid orbital I am going to project in this manner. Rest of the 3 will be projected in this direction. So now you see here, this is the upper sp3 orbital. This sp3 orbital I am writing here. And remaining sp3 orbitals I am writing like this. These are all 4 sp3 orbitals. So each of the sp3 orbital is occupied by the 1 electron coming from those unpaired electrons. This is of 1 carbon. Another carbon atom also participates in the same hybridization. So the sp3 orbital of 1 carbon atom overlaps with the sp3 orbital of the another carbon atom to give the carbon-carbon sigma bond. And these are occupied by the 1 electron each. Now every sp3 orbital of every carbon atom overlaps with the 1s orbital of the hydrogen so that they can produce the total 6 carbon hydrogen sigma bonds. So here we can write down that with 1s orbital of the hydrogen, they give the 6 carbon hydrogen sigma bonds. Its equivalent structure we can write down like this: carbon single bond. Now you can imagine the tetrahedral shape if you view the molecule from this direction. The bond angle here is 109.5 degrees. Carbon-carbon single bond length is 154 picometers. Carbon-hydrogen bond length is 109 picometers. And what is the percentage of the S character here? So percentage of the S character is 25%, and percentage of the P character is equals to 75%. Then how to imagine these are the tetrahedral? See here 2 tetrahedral units are present. So when you connect this bond up to here and like this, so this is one tetrahedral unit and this is another tetrahedral unit. So altogether 2 tetrahedral units are present in the one ethane molecule. Now let us compare the bond lengths, bond angles between the ethane molecule, ethylene molecule and ethane molecule. CC bond length order. Carbon-carbon single bond if carbon participates in sp3 hybridization. Carbon-carbon bond if sp2 hybridization both. Carbon-carbon bond if sp hybridization is there. So sp2 means obviously there shall be double bond. Sp means obviously there shall be triple bond. So carbon-carbon single bond length is 154 picometers, and in this case it is 134 picometers, and in this case it is equals to 120 picometers. So when the percentage of S character and P characters, when you observe that, in this case percentage of the S character is 25%, whereas P character is 75%. Here it is 33.33%, 66.67%, and here 50% both. So when the percentage of the S character increase, gradually the bond length decreases. So that the bond length is more for the carbon-carbon single bond than the double bond than the triple bond. When the carbon-hydrogen bond lengths are observed, carbon-hydrogen bond length with sp3 carbon, with sp2 carbon, with sp carbon. Here it is equals to 109 picometers. Here it can be taken as 108 picometers. It is approximately equals to 106 picometers. So again here also the bond length order is sp3 carbon hydrogen bond length is more than the sp2 carbon hydrogen and later than the sp carbon hydrogen. And remember one thing, that whenever carbon forms all single bonds, it always participates in the sp3 hybridization. Whenever carbon forms one multiple bond or one pi bond is present, then its hybridization is sp2. Whenever carbon forms a triple bond or two double bonds, then the hybridization of that carbon is equals to sp. Let us see some examples in this case. CH3, CH2, CH double bond, CH and CH3 is there. If you see the hybridization, carbon all single bonds, here carbon double bond is there. Hence hybridization of this carbon is sp3, here sp3, here sp2, here sp2, here sp3. Total number of hybrid orbitals. Total number of hybrid orbitals means just add the number of hybrid orbitals here. sp3 means 4 orbitals are there. 4 plus 4, 8. 8 plus 4, 12. 12 plus here 3 plus 3, 6 are there. So 6 plus 12 is equals totally 18 hybrid orbitals are present. Total number of pure orbitals, or we can call this one as the unhybrid orbitals, means the atoms are having the orbitals but not participate in the bond formation. So this can be calculated for the hydrocarbons as number of hydrogen atoms plus 2 into number of pi bonds. Now if you see these hydrogen atoms, here 3 plus 2, 5, 6, 7 plus 3, 10 hydrogen atoms are present. 1 pi bond is present. So that 2 into 1, that equals to totally 12 unhybrid orbitals are present. So how these unhybrid orbitals are coming? Reason is 1s orbital of hydrogen don't participate in the hybridization. Just it participate only in the overlapping with the hybrid orbitals of these carbon atoms. That means 10 hydrogen atoms are giving the 10 1s unhybrid orbitals. And pi bond is formed by the unhybrid orbitals but not with the hybrid orbitals. That means one pi bond formation requires 2 unhybrid orbitals or pure p orbitals. That's why 2 into number of pi bonds, totally unhybrid orbitals are equals to 12 are present. Let us take one more example. CH2 double bond C double bond CH2. The molecule is called as alene molecule. So in alene molecule, this is SP2 hybridization, this is SP, and this is SP2 hybridization. This carbon forms only double bond, hence SP2 hybridization. This carbon also forms only double bond, hence SP2 hybridization. This carbon forms, see, two multiple bonds are there, two double bonds, hence hybridization is SP. So what could be the total number of hybrid orbitals? 3 plus 3, 6 plus 2, 8. 8 hybrid orbitals are there. Unhybrid orbitals, how many are there? 2 and 2 hydrogens. Totally 4 hydrogens plus 2 into number of pi bonds. Here 1, 2. So 2 into 2, 4 plus 4, again 8. So in this case, equal number of hybrid and unhybrid orbitals are present, so that the ratio is also equal. 8 by 8, that means 1:1. Let us take this molecule. And if you find out the hybridization, SP2 hybridization, SP2 hybridization, SP and SP. So here hybrid orbitals 3 plus 3, 6, 6 plus 4, 10 hybrid orbitals are present. Unhybrid orbitals, how many are there? Hydrogens 2, 3 plus 4 plus 2 into, here 2 pi bonds, here 1 pi bond. Totally 3 pi bonds are present. So this is 6 plus 4. Again 10. In this case also, the number of hybrid and unhybrid orbitals are equal. Dear students, I hope you understand today's class. If you really understand my classes, please do like and share with your friends. And do not forget to subscribe the classes. Thank you one and all.